Apparently, all right, here we go. This Chem 30 lesson today is on metallic bonds. We're going to be talking about ferrum 0026, special agent, hard case to crack, metallic bond. You've heard of my cousin James Bond. My name is Metallic Bond. Anyways, we talked about ionic bonds and covalent bonds. This is not the same as a covalent bond, although it's similar. Remember, covalent bonds are equal sharing of electrons. You'll find today that the metallic bond is something very special, and it's what gives metals its properties. So, metallic bonds are formed when the same metal atoms are bonded together. Like if we have a solid piece of iron, special agent 0026, solid iron, okay, or copper. If we have a copper pipe, right, that's made purely of copper, let's say. And so we have atoms that are bonded together by special bonds called metallic bonds. So when the same metals are bonded together, that's when we have metallic bonds. That's what we're going to focus on here today. These bonds are characterized by electrical conductivity. So if you think about copper pipes, copper wire, not copper pipe so much, but copper wire, right? Luster, do you know what luster is?
Sure.
Yeah, luster is shininess. And malleability. Who knows what malleability is? Yes, bending. Yes, it's sort of the property that metals would have that they can change shape, so you can kind of hammer them into shape, and they are bendable and stuff like that. So obviously copper wire, it's pretty good idea for copper wire to be bendable, right? Because it doesn't go in a straight line always. I mean, it's got to wrap around things and go through walls and different channels, right? Okay, metals in the solid state form crystals. And electron clouds overlap. Okay, electron clouds overlap quite consistently, which means throughout the material. This forms a delocalized electron cloud, okay? And when we talk about delocalized, we're not talking about electrons that are specifically centered around certain atoms. It's like a cloud that encompasses many atoms. It's like this huge cloud and this huge array of atoms, and it's almost like one. It's not separate clouds for each atom. It's kind of like well, you'll see it's kind of like this big envelope, and electrons are not specifically bound to one atom. And because of this, electrons are free to move around. Okay. And this is what contributes to the high conductivity. All right. Also, these electrons in this delocalized cloud react readily with light, causing the high luster. Apparently, the spell check does not like the French version of luster, but anyways. Okay. So atoms can rearrange themselves quite easily because of this delocalized electron cloud, which causes the high malleability. So because it's not a rigid structure so much, these atoms can kind of slide around each other and position themselves just a little bit different because the electrons are not getting in the way. The electrons are, they're not bound to certain electrons. So it's almost like if you look at on the atomic level, it's more of a fluid sort of thing, right? There's these little pebbles in this pudding, right? And so you can move those pebbles around pretty easily, but they can rearrange themselves easily because of these delocalized electrons as well. And that causes the high malleability. Okay, so there's some characteristics and some explanation of the characteristics. We're going to get into the hardness of metals soon here, but electrical conductivity, luster, malleability, it's all because of this metallic bond. I want to talk to you a little bit about hardness of metals. And I don't know if you've noticed, but metals in the pure state, lots of metals we have today in rings and metals that are making up our instruments that we use, the desks that you're sitting at, the chair legs and that sort of thing. Those metals are not pure. They're not one element. They're a mixture of elements, which makes them very strong. And so when we're talking about pure elemental metal, like let's say we have sodium metal, you may know that sodium is very reactive, but it's also very soft. It's very, very soft. So this is a little video clip of sodium metal in water. You don't get to see the actual sodium here, but this is just a bit of a slow motion picture. When sodium metal is in contact with water, even if it's in contact with the moisture in the air, there will be some heat generated, some reaction generated. It's very, very volatile. So we'll just watch a little clip on the volatility first. So this is sodium that's just been placed in water, and it reacts quite violently. Picture there, so a little bit closer here. So it was just in the corner there, you see that? This is a chunk of metal. Hello. Okay, good, I'll get that for you. So that's how violently sodium metal reacts with, and that's just water. It's just a little bit of sodium metal with water. Okay, so here's a picture of sodium. Obviously the knife is harder than the sodium because it's cutting through. And yeah, it would be like, sort of like cutting through frozen butter, I guess, similar. Okay, so that's kind of the hardness of sodium. You would think that all metals are hard, but they're not in their elemental state. Group 1 elements like sodium, okay, have one outer electron, so it's one valence electron, and they are very soft. Group 2 electrons, so the alkaline earth metals, beryllium, magnesium, calcium, strontium, and so on, they're a little bit harder. They have 2 valence electrons, right? Group 2 is a bit harder. The transition metals, once you move sort of towards the right from the far left of the table, the transition metals, those are characterized by the d electrons, right? They all have d electrons. And these transition metals are often quite hard because of the overlapping d orbital electrons. So there's some electrons in the d orbitals, and they actually sort of a deeper level of, there's more participation in this metallic bond. And if you think about metals like titanium, iron, copper, nickel, silver, gold. I mean, gold is really in its elemental form. It's actually still pretty soft. I mean, it's not like alloys are really strong. So gold mixed with something else has quite a bit of a stronger bond, and it's pretty hard. That's why if you have a ring that's 10 karat gold, okay, it's got some gold in there, but it's mixed in with some other metals to make it stronger. If you've got a 24 karat gold ring, you could probably squish that ring in your fingers. You could just squish it right down flat. Like if it is pure gold, it's pretty. You guys saw I had my my championship hockey ring yesterday. That ring has got a lot of gold content in it, and I dropped it on the sidewalk once, shortly after I got it, and picked it up, and there you go. There's a dent, right in the letters there. ECAC champion, dent. Okay, well that's good. So anyway, so yeah, you just drop it. It's quite soft actually. So the more pure they are, I mean, these are still harder than sodium. A sodium ring wouldn't be very good. First of all, you blow your finger off, all the moisture in your hand, but wouldn't be so good. Okay, questions? The thing that I want you to write down here for these notes is that the metallic properties decrease rapidly from from groups 13 to 16. So group 13 to 16, if we take a look back at the periodic table, I'll give you a chance to write that down in a second. So group 13 is right here. You see that? There's group 13 right there, and 13 to 18. So obviously, these would be considered the non-metals in this top right corner, right? Non-metals. And so we still have some metallic properties, but these metalloids here, they're really losing their metallic identity a little bit, and they're sort of half metallic and sort of half, they're not sure, right? And so as we move to the right, generally, the properties, the metallic properties drop off quite a bit. Okay. All right. So in your textbook, there is a chart on page 311, And what I want you to do is I want you just to take 10 minutes or so, 15 minutes, I don't know how long it'll take you, but I want you to copy that chart into your notebook. Yes, there's something in print that you have access to that I want you to recopy. The reason why I want you to do that is because as you take this time, and I don't want you to be talking about movies and other situations here while you're doing this, I want you to focus on what you're writing. I want you to, in your mind, get this organized. What a covalent bond is generally formed between. How is it formed? What are the properties of that bond type? And what are some examples of substances? So I want you to copy that chart into your notebook. I'm just giving you some nice, peaceful, quiet time here to do that. And I'll try and find a chart and pop it up here on the screen for you a little bit later. I don't have a copy of this exact one, but just take some time to study these bond types this way by copying that chart. All right, so as we just continue our last little bit of notes here on polyatomic ions, you guys know what polyatomic ions, they are ions that have more than one atom, right? Poly, which means more than one atomic ion. So they're an ion that is not a monatomic ion, but poly. Hydroxide is one example. But in these polyatomic ions, there's some interesting things that happen there. We have covalent bonding happening in the polyatomic ion. And so at least one covalent bond exists between the atoms in the polyatomic ion, although the particle as a whole has an overall charge. And so there's some common examples, I think, in page 169 there. You see a bunch of common polyatomic ions. But if we use hydroxide as an example, the O and the H, if you'd like to take a look at their electronegativities, their bond would be a covalent bond. But because oxygen still has some unpaired electrons, the overall charge of the particle is negative. And these are the electrons that will bond with a metal in an ionic bond. So if we talk about sodium hydroxide, for example, sodium is really ready to give up its electron, ready to give up its electron. OH will want to steal that electron to become negative, and so on, and so we'll have that bond there. So that's just a little bit about polyatomic ions. You'll have a question about that in your assignment. And you may be interested in reading this Alien Alloys on page 312. Just an interesting read. All right, so you copied that table already, and here's the next little bit of information I'm going to give you. On page 317, I want you to do these questions just from chapter 12, just from the material that we've talked about in chapter 12. You do have some time to work on them in class here. Page 317, 14 to 16, and 22. And as well, Unit 3 here, the material science, is going to be split up into 2 exams. The first exam is going to be on chapter 4, 5, and 12, which we have just covered. Chapter 4 began with the history of the atom, so that assignment, that's where we started with that. Chapter 5 is electrons, and then chapter 12 is bonding and stuff here. So that's going to be your first exam. I'll set a date for that, but you can anticipate, that coming in a week or so. Towards the end of next week, you can anticipate an exam because we're done that material now. So it'll be just reviewed from here on out. We may be starting the next little bit of stuff, but we probably will give you a chance to study after we've started some newer material. But you should plan for the exam in about a week.